A sample of xenon is analysed in a time-of-flight mass spectrometer. The sample is ionised by electron impact and forms 1 plus ions. So electron impact, 1 plus ions. Give an equation including state symbols to show how a sample of xenon is ionised in the time-of-flight mass spectrometer. So we have xenon atoms in the gaseous state symbols. That forms xenon plus ions in the gaseous state, and there's the electron that has been knocked off. Okay, table 1 shows data about the 4 peaks in this spectrum. Give the symbol including the mass number of the ion that reaches the detector first. So that's going to be the lightest one, or the one with the lowest MZ values. That's going to be that one. So the symbol, xenon, mass number, 129, and then it's an ion, so I need a 1 plus charge on here. And I'm told earlier on that it forms 1 plus ions. Part C, calculate the relative atomic mass of xenon in this sample, giving your answer to 2 decimal places. So I'm just going to give myself a little reminder down here. And I've got this abundance to calculate. So in order to calculate that abundance, it's going to be 100 minus and that equals 26.65. So there's going to be a mark for that. I now use my relative atomic mass formula. So that equals, let's get the table up there. So 129 times 27.8 plus 131 times 25.55 plus 132 times 26.65, that's the one I've worked out, plus 134 times 20, divided by the total abundance as its percentages, this is 100. That gives me 131.3105 to 2 decimal places. That is going to be 131.31. So 1 mark for the working, another mark for the final answer there. Part D, explain how ions are accelerated, detected, and have their abundances determined by the time-of-flight mass spectrometer. So they are accelerated using an electric field. So that's the first bit done. Detected, so they are detected when they gain an electron. And remember, this makes a current. And then the abundance is the size of the current is proportional to the abundance. Okay, E. In a time-of-flight mass spectrometer, ions are accelerated to the same kinetic energy. The kinetic energy of the ion is given by the equation there, where kinetic energy is in joules, mass is in kilograms, velocity is in meters per second. In a time-of-flight mass spec, so I can get the mass from that. I've got the distance of the flight tube, and I have the time of flight. Calculate the kinetic energy. So to get the kinetic energy, I need this. So I need to calculate my mass and calculate my velocity before I can do that. So let's start with the mass of the ion. So mass is 131. Now that's grams of a mole. So let's turn it into kilograms by dividing by 1,000. And then let's get the mass of one ion by dividing by Avogadro's number. And that gives me 2.175 times 10 to the minus 25. The kinetic energy, actually I need the velocity first, So velocity is the distance divided by time, so that's 1.15 divided by 1.72 times 10 to the minus 5, which equals 66860. Now I can work out my kinetic energy from that. So kinetic energy is equal to a half times the mass times the velocity squared, which equals 4.86 times 10 to the minus 16. So 4.86 times 10 to the minus 16. So there's the marks for working out the mass, marks for working out the velocity, marks for putting the numbers in the formula, and then 1 mark for the final answer.